A compliance officer asks an AI system whether a specific procurement action violates federal acquisition regulations. The system returns a confident answer. The next day, the same officer asks the identical question. The system returns a different answer. Both responses are plausible. Neither is identical. The compliance officer needs to know which one is correct and why the system disagrees with itself. This is not a bug. It is the expected behavior of a stochastic system being used in a context that requires deterministic precision. The problem is not the technology, it's the architectural mismatch between what was built and what the domain requires. This is Stochastic versus Deterministic, Why Your Retrieval Strategy is an Architectural Decision. ML, Part 21. Why the choice between probabilistic and rule-based reasoning determines what your machine learning system can and cannot be trusted to do. In Part 12, we covered how concept drift changes the relationship between inputs and outputs over time. Stochastic versus deterministic reasoning is the upstream architectural decision that determines how your system handles uncertainty before drift ever becomes a factor. Section 1. What deterministic actually means in production. A deterministic system is one where the same input always produces the same output. A Sparkle query against a knowledge graph is deterministic. Given the same graph state and the same query, the result is identical every time. A rules engine evaluating a compliance policy is deterministic. The rule either fires or it does not based on explicit conditions that do not vary. A SQL query against a relational database is deterministic. The rows either match the predicate or they do not. Deterministic systems are auditable by design. You can trace every output back to the exact inputs and rules that produced it. You can replay any decision and get the same result. In regulated environments where auditability is a compliance requirement, determinism is not a preference, it's a prerequisite. The limitation of deterministic systems is brittleness. They can only answer questions their rules anticipated. They cannot generalize to novel inputs. They cannot handle the ambiguity and natural language that characterize real-world operational data. A rules engine that handles every procurement scenario your legal team anticipated fails silently on the scenario nobody thought to write a rule for. Section 2. What stochastic actually means in production. A stochastic system produces outputs drawn from a probability distribution rather than a fixed mapping from inputs to outputs. Large language models are stochastic. Given the same prompt, they sample from a distribution of probable next tokens, which means output vary across runs even with identical inputs. The temperature parameter in most language model APIs controls how much sampling variance the system introduces. Lower temperature produces more deterministic outputs. Higher temperature produces more creative and varied ones. Machine learning classification models are stochastic in training, where random initialization and sampling affect what the model learns. Machine learning classification models are stochastic in training, where random initialization and sampling affect what the model learns, but largely deterministic in inference once weights are fixed. Neural outputs with dropout layers remain stochastic at inference time as a regularization strategy. Reinforcement learning agents introduce stochasticity in action selection as an exploration mechanism. Stochastic systems generalize where deterministic systems break. A language model can answer a question phrased in a way no rule anticipated. A machine learning classifier can handle an input pattern it had never seen exactly, but that resembles patterns in its training distribution. That generalization capability is why stochastic systems dominate modern machine learning, despite the auditability challenges they introduce. Section 3. Where RAG sits between both worlds. Retrieval augmented generation is the architectural pattern that most directly confronts the stochastic versus deterministic tension, and it is worth understanding in depth because most production, knowledge-intensive machine learning systems are moving toward it whether they label it RAG or not. The insight behind RAG is that large language models are stochastic generators without knowledge cutoff. They learn patterns from training data that ends at a specific date. They cannot access current information. They hallucinate when asked about specific facts outside their training distribution. These are fundamental limitations of stochastic generation that cannot be solved by making the model larger or training it longer. RAG addresses these limitations by separating retrieval from generation. When a query arrives, a deterministic retrieval layer searches a knowledge base, a vector database, a document store, or a knowledge graph for relevant information. That retrieval is rule-based and repeatable. The retrieved content is injected into the language model's context window as grounding material. The language model then generates a response conditioned on that retrieved content rather than relying purely on learned weights. The retrieval layer is deterministic. The generation layer is the stochastic. The combination produces systems that can generalize across natural language variation while remaining anchored to verifiable retrieved facts. When the system produces a wrong answer, you can trace it to either of a retrieval failure, the right documents were not found, a generation failure, or the model represented what the document said. The traceability is what makes RAG architectures audible in ways that pure stochastic generation is not. The database choice underneath the retrieval layer determines how semantically precise the retrieval can be. Most production RAG implementations use vector databases that retrieve documents based on embedding similarity. A query is converted into a vector. That database returns documents whose vectors are closest in embedding space. This is fast and effective for broad semantic similarity, but it is itself a stochastic operation. Two similar queries may retrieve different documents depending on how their embeddings land in vector space. This is where the semantic layer we have been building across the series becomes directly relevant to RAG architecture. The majority of database choices in production environments are not natively semantic. Relational databases, document stores, and even most vector databases do not understand what data means. They retrieve based on structural similarity, keyword overlap, or embedding proximity. Injecting a knowledge graph with formal ontological structure into a retrieval layer of RAG system gives the retrieval step something closer to meaning-based precision rather than pattern-based approximation. A Sparkle query retrieving triplets relevant to a compliance question returns exactly the assertions that match the formal query conditions, not the most similar documents, the factually relevant ones. The architectural decision is therefore not binary between stochastic and deterministic, but a design question about where you place each approach in the pipeline and what retrieval substrate grounds the stochastic generation layer. Organizations that push all the semantic heavy lifting into stochastic generation layer, asking the language model to figure out what things mean rather than retrieving predefined meanings, are trading precision for convenience in ways that compound in high-stakes domains. Section 4. Choosing the right approach for the domain. The decision framework is simpler than the architecture suggests. Ask two questions about your domain. First, can you tolerate output variance? If the same query must produce the same answer every time for compliance, audit, or safety reasons, the stochastic layer must be constrained or eliminated for that query type. Deterministic retrieval with templated generation or pure rules-based response for specific query classes preserves auditability where it matters most. Second, can you tolerate brittleness? If your system must handle natural language variation, novel query formulations, and inputs that no rule anticipated, pure determinism will fail. The stochastic layer produces the generalization that makes the system useful across the full range of real-world inputs. Most production systems need both answers to be no, which means hybrid architectures that apply deterministic retrieval over formally structured knowledge for precision-critical queries and stochastic generation for generalization-critical responses. The challenge is knowing which query type you are handling at runtime and routing accordingly. Section 5. Why this matters. The compliance officer in the opening scenario is not an edge case. Any domain where decisions have consequences, where audibility is required, or where a wrong answer has a cost beyond inconvenience, and where it hurts is the difference between building machine learning systems that earn operational trust and building systems that demonstrate impressive demos but fail compliance review. In part 22, we will examine grounding and entailment, the mechanisms that connect stochastic machine learning outputs to verifiable facts, and why anchoring predictions to the knowledge layer is what separates a system that reasons from a system that guesses.